Carrying on with our Rotorcraft theme this mid-morning. Next up is Ed Smith and also Dr. Eric Greenwood, and they'll talk about the work going on in our Rotorcraft Center. Microphone's up there, and there's a clicker.
All right, good morning, everyone. It's always a pleasure and enjoyable to come back to the CAV workshop. We've had our group on Rotorcraft, Acoustics, and Dynamics for many, many years. It's kind of a difficult application. We're always interested in things that CAV is doing, so we like to share some of our activities with you as well. I'm Ed Smith. Again, I'm a professor in the Aerospace Engineering Department. When we talk about Rotorcraft, just to set the stage, we have many different configurations of vehicle, some of them having one large rotor in the center of the vehicle driven by multiple engines with a gear reduction. So on the previous presentation, you saw those gearbox tones. We have a combination of military aircraft up there on the top of different sizes and weights. Some of them have the engines and gearboxes out at the wingtips, and some of them have them more centralized near the cabin. You can imagine the impact on noise depending on where those gears are located. On the lower right, we're seeing an increase in the interest in the community at large in what's called an air taxi, which is largely an electric driven vehicle. In some cases, it's a hybrid electric-driven vehicle with multiple rotors that hovers for a fairly short amount of time and then cruises for a somewhat short range, delivers passengers and cargo, and then recharges its batteries. So this is something envisioned for the future in 21st century transportation, especially in urban areas. And as you can imagine, there are a lot of noise questions associated with acceptance from the community, and there are also some related to passenger comfort. The spectrum of Rotorcraft, Acoustics, and Dynamics is pretty wide. This afternoon or this morning, we'll be focusing on the top rotor noise, rotor external noise. So I won't talk about all of the other things across the frequency spectrum. Etienne mentioned some of the sources for vibration. So over the years, we have a lot of different activities throughout this frequency range, but today we'll narrow it and focus it on the rotor noise at the very top. We have a number of group members. There's 3 or 4 of us. Several of us are in the room who focus on Rotorcraft almost exclusively in our research and education, and then we enlist a number of other subject matter experts, and there's quite a bit of overlap between our interests and our needs and the CAV expertise, both experimentally and simulation. So we have, over the years, a number of faculty members in different departments. Eric Greenwood is highlighted, and I'll talk about Eric and embarrass him a little bit, and then turn the podium over to him in a minute or two. We've had a number of students working with us. We have about 50 graduate students matriculating through the program in rotary wing engineering here. Of course, some of them work on noise and vibration. Others work in different disciplines like aerodynamics or flight controls or propulsion and so forth. And you've heard from a number of these students over the last several years, and it's good to say that they're employed throughout the industry and the government laboratories. And these theses make their way onto the CAV website in kind of a real-time basis as soon as they go through the Penn State system. So if you have further interest in any of the details and you're poking around the website, you can find a lot of different dissertations that may be of interest. We have a number of current graduate students on this list, more for your reference. I won't go through all of these, but hopefully we'll hear from these students as their research progresses in the next several years. We've been working for the past 5 years on our VLR-CO's Vertical Lift Research Center of Excellence. That's our main program that's supported by the DoD and NASA here. There are a number of research projects. These are the ones that are coming to a close. Some of them we continue to work on, and these are the ones that you've heard over the years, so I don't want to spend any time on those other than to refer you to theses in these areas. I want to give most of the time to Eric and to mention about our new program. The new program was a very competitive process. It goes on every 5 years. We were supported again, we found out in the summer, so that gives us another 5 years and quite a bit of resources to hire students and pay for equipment and so forth. And Eric Greenwood, Professor Greenwood, will explain to you some of the new projects that we'll be starting in a few moments. There's also a web link for you that gives a whole list of the projects and some more background. Eric Greenwood is here for the last couple of years on our faculty as assistant professor of aerospace engineering. Prior to that, Eric spent about 10 years at NASA Langley in the noise aeroacoustics branch, so he comes with a lot of momentum and a lot of background. We were delighted to have him join our faculty. Eric did his graduate school down at the University of Maryland, working in aeroacoustics. That's one of our counterpart vertical lift research centers. So we were again very happy to recruit him and have him join our group. We expect to see many great things from him to come. So let me turn it over to Dr. Greenwood, and he can talk to you about, I think, 3 of our new projects coming on.
Thanks, Ed. Yeah, so it's very exciting for me to be involved in some of these new acoustics tasks, especially having kind of come up through the vertical lift education system myself. So I just wanted to present 3 of the tasks that we have that are primarily focused or largely focused on acoustics. So the first one here, I'm not directly involved with. The task leads for this are Sung-Kyu Lee, who's currently a professor at UC Davis and also a graduate of this program, and Professor Ken Brentner here. And this is actually an interesting problem. I am quite familiar with it indirectly, you know, from my time at NASA when we had the opportunity to take some noise measurements for tilt rotor. And you know, there's some interesting things that are going on when you take a close look at that data. And you know, we have lots of computational experimental evidence now that there are some strong aerodynamic interactions that happen between the prop rotor, say on the V22, you can see there in the lower right corner, and the airframe and the wing, right? As compared to, say, a turboprop aircraft where the propellers are relatively small diameter and they're out on nacelles, there's not really room for that on most tilt rotor configurations. So the rotor diameter is quite big and it's very close to the body, right? So these interactions are stronger than we're used to on a lot of aircraft. And really the effects of these interactions on the noise, on the vibrations, on the performance, they're not that well understood. So, you know, we would like to be able to, you know, equip the designers of future tilt rotor and tilt wing aircraft, say something like the NASA GL-10 up there, with some better knowledge of the governing physics here and some medium fidelity design tools, things that don't require, you know, supercomputers to run, something you can use for conceptual design to figure out how to design efficient, low noise tilt rotors and tilt wings. So just to kind of give you some idea, sort of a flavor of the work that is out there, this comes from a study by Jun Lin, the Army, where they started, he was looking at high fidelity CFD computations of this prop rotor wing interaction. And there's really 2 kind of phenomena that govern this. One is the, shown there on the top, I have the wing actually displaces some fluid flow around it, right? And that displacement of the flow causes, you know, basically an unsteady loading to occur on the big prop rotor in front of it, right? And another thing that we have there on the bottom, it says wing loading, right? The wing itself, in the act of generating lift, it has a circulation around it. So there's an upwash ahead of the wing and a downwash below the wing or behind the wing. And that generates a very different form of unsteady loading, right? And then the combination of those two is going to give us some unsteady loading on the Proprotor. And anytime we have unsteady aerodynamic loading in Acoustics, especially when things are moving quickly, as they are in the rotor, that's going to relate to the generation of noise. So there's an earlier paper here with Jinhua Zhang, Ken Bretner, and Ed Smith that was looking at some mid-fidelity predictions of this Proprotor wing interaction and the impact on acoustics. And here are just two polar plots. So you're looking from the top down on the noise that's radiated by the aircraft. It's moving towards the left, and I realize now I neglected to label these, but the one on the left here is showing us just the acoustic radiation, both thickness and loading noise, for this Proprotor in an isolated kind of configuration. And then the plot there on the right is showing when I bring that Proprotor close to a wing, in this fully configured aircraft, the overall sound pressure level polars. And you can see there's a dramatic increase in the noise, especially up and down the axis of the aircraft. So, I'm dramatically increasing the noise that's being radiated ahead of the vehicle, which could be, a big concern if I don't want to hear people hear me there. Now, June, in his paper, also took a look at what using a high fidelity calculation, what the effect of the Proprotor was on the wing, right? As opposed to, we have this close coupling. It's not just the wing affecting the Proprotor, but the Proprotor affects the wing. When he took a look at the loads on the wing, and this is basically a plot on the y-axis, we're looking down the semi-span of the wing, so the bottom there is close to the vehicle. As we get out towards 1, that's towards the wingtip. And you can see the loading fluctuates quite dramatically over time, all right, especially right where those Proprotor blade tips pass near the wing. And on the right, for emphasis, we've kind of removed the mean value of the loading, and you just see this unsteady loading. And the thing is, right, this will, of course, have some impact on the vibration that we feel through the structure, and it's going to have an effect on the performance, because those are pretty big in magnitude, actually, that unsteady perturbation compared to the mean. But this is a big radiating surface, too, right? So the wing has an enormous amount of area. So even though it's maybe not moving at a high Mach number, we have quite a lot of unsteady loading distributed over an area. And whether you want to call that an aeroacoustic phenomena or just really a realization of acoustic scattering off of that wing, it still has the potential to also have a significant impact on the noise. Problem, right, is that to get this prediction, you have to run right now a CFD calculation on a big DoD supercomputer. And really the goal here is to find a way to build kind of a mid-fidelity model that you could use when you're trying to design a two-tilt rotor that would be able to replicate similar physics. So moving on to another one of these acoustics tasks. So this is one that I'm working on along with another kind of recent hire in the aerospace department here, Mark Miller, and then Jose Palacios has another presentation following this. And here we're looking at this idea, right? We are very concerned with these acoustic interactions. Just for an example, I have a chart here showing a wake model from CDI's CHARM, and I've highlighted all the possible interactions. We have that kind of rotor-wing interaction I was just talking about, but also interactions between rotors on these new air taxi type vehicles and props and so on. And what makes it really challenging for us is a lot of these interactions happen at a long wake age. Or in a sense, the vortices are created by upstream propellers. They don't interact with anything until they're far downstream. So they get quite turbulent. It's very, very hard, even with high fidelity codes, to predict this kind of phenomena accurately over that amount of time. So we need some more experimental data in order to model this. But our experience with helicopters tells us that if I'm going to take experimental data, it's very difficult to scale things down to a smaller scale. I run into a limit, it's about maybe 1/7, 1/5 scale for a helicopter rotor, which means that I need a pretty big facility if I want to take measurements in the acoustic far field, right? So down there's a plot of a photograph of the NFAC, the largest wind tunnel in the world, where they do a lot of aeroacoustic studies for Rotorcraft, and even there are facility limitations, right? So we want to try to come up with a way that especially for these complex configurations, we can collect scaled acoustic data and performance data for these multi-rotor configurations without requiring enormous, one-of-a-kind facilities to do that. Basically our idea here, I should go back, right? We're going to, investigate this sort of scaling and then try to come up with some scale correction strategies that we can use. So we have a facility, some of you may be familiar with this, it's been used extensively, particularly for jet noise measurements. Here it's an anechoic chamber with a small scale wind tunnel that passes through it. It's got a 2x2 opening when we open it up to its widest configuration. And we've recently, working with Jose Palacios here, have developed a pretty unique multi-rotor testing capability, right? And this is nice in terms of looking at these interactions because we have multiple test stands. We can put a pair of rotor really in any orientation relative to each other that we want to explore these aerodynamic acoustic or aeroacoustic interactions with, say, up to 18-inch diameter rotors, right? We've got a traversing microphone array. We can get a good range of measurements at different directivity angles. So you can see it's real. That's a photograph of the apparatus, again with our microphone array and the multiple rotors. Those of you who are taking the short course tomorrow will get a chance to see some of this in person. So that kind of gives us our small scale. At large scale, Jose has also been building up a 8-foot diameter rotor test stand, give or take. Sort of in my research group, we're doing a lot of outdoor noise measurements. Over here on the right, we have some things we've been working with Beta Technologies to take noise measurements of their vehicle. That's actually their rotor test stand, so also about 8-foot diameter. We've collected some full-scale data for their rotor and hover, as well as for their vehicle flying. And so that we can get, at least for hovering conditions and things like that, and working with some industry partners, some full-scale data. And then really the trick here to try to reconcile the two is what is sort of this noise scaling theory that's been developed. So if we start with our Fox-Williams-Hawkins equation, right, we can non-dimensionalize that as we do as good engineers, and then turn this into a non-dimensional form like we see below. And if I look at this equation here, I basically have the acoustic pressure as a function of basically rho c squared, or the proportional to the ambient pressure. And I can get that as long as I match the non-dimensional aerodynamic operating condition on the right-hand side. And the problem I have here is I've got 5 parameters, advance ratio, angle of attack of the rotor, tip Mach number, thrust, of the rotor, and the Reynolds number on the right-hand side, and I can, at most, in regular air, match 4 of them, right? However, if I somehow were able to change, say, the density of the air, I could then adjust the thrust coefficient, the Reynolds number, on the left-hand side ambient pressure, and I could make this scaling work without having a Reynolds effect. And fortunately here, Mark Miller has been building up this compressed air wind tunnel that is designed exactly to do this, to give us aerodynamic similarity up to maybe 34 atmospheres of pressure, right? And as I increase the pressure, the density increases almost proportionally to that. So I should be able to get exact aerodynamic scaling, say for an 18-inch rotor in this tunnel, to correspond to something like a 51-foot rotor, or like a full-scale helicopter rotor, without sacrificing anything in terms of Reynolds number. This kind of stuff has been well explored for things like wind turbines, but we're trying to apply it now to higher tip Mach number rotors, and we want to look at acoustics. Taking acoustic measurements under high pressure is a little new. We don't have great understanding of how the microphones perform, especially up at 34 atmospheres or higher. Some of the anechoic materials. So we've been doing a lot of groundwork, building kind of custom calibration equipment so we can verify the response of the microphones, verify how well the anechoic treatment works. So we're really excited about this ability to try to bridge the gap between small scale and large scale. And then the last thing I wanted to talk about was this another task here with myself, Jack Langelon, and Ken Brentner on acoustically aware aircraft, right? And so our experience with helicopters, because the rotor is so sensitive to changes in operating condition, right, we have a lot of ability to control the acoustic impacts by adjusting the flight operations of the vehicle. So here's an example of a plot, something like from the HAI Fly Neighborly Guide. I can put a region on the map that shows a helicopter operator what speeds and rates of sync are going to be noisy, and then they can come up with some approach to work around that. Unfortunately, the research, we've learned a lot more about this in maybe the last decade or so, so a lot of the work I did previously at NASA. And that noise point is really, again, because of changes in the aerodynamic operating condition, affected by things like the weather, the weight of the vehicle, how it trims out, the drag in the vehicle, right? It's very specific to the time when I'm doing that operation and what I'm trying to do, right? So moreover, a lot of our experiences, say like the HII Fly Neighborly operations, has showed that they can be limited by things like the weather, right? If the ceiling is lower because I've got cloud cover, I might not be able to fly in as steep a rate of descent as I'd planned. So I really need to be able to provide guidance at the time of use, not based on some pre-calculated, pre-looked up kind of work. So that's the idea here, is how can we get on-the-fly noise abatement guidance and really even embed it into the autonomous system of the aircraft so it can fly more quietly. So we've done a little bit of work on this area. Been developing a code to do quick noise predictions, where you can do basically take some measured data, use that to calibrate some experimental models and build up a database all offline of the noise radiation characteristics of that vehicle, say as a function of a bunch of hemispheres. And you can take all the time in the world to do that. And then when at the time of use, right, I can now just look things up from that database, scale them appropriately using the same sort of non-dimensional parameters I talked about before, and predict the noise on the ground. So this is an example comparison for an S-76 helicopter of the sound exposure level contours for an approach. Top is a measured data, the lower portion is a prediction. We're able to use the predictions in this case to help NASA out by extending where we could put that acoustic array, essentially. So this same model has been used, another project worked on with some folks at NASA still, for real-time noise prediction from a helicopter. And this is really has been used as a noise training aid to help pilots figure out what to do to fly more quietly. We got very good positive feedback from this when we've taken it to operators, but it's not something you'd want to be staring at while you're trying to safely fly the helicopter in real life, right? It's good as a training aid. So what we'd like to do is have the autonomous system take over for that mental effort of how do you fly quietly while you're trying to execute the mission. So the approach there one of the approaches that we're looking at is, well, if I have this fast model, maybe I can pre-compute some different maneuvers. So here's an example of something like a turn. And if this only takes a few seconds to compute one individual maneuver, maybe I can compute all the sorts of maneuvers I might want to fly, and then kind of, at least in my mind, I view this as connecting them together like Tinker Toys to build a path that gets me from where I am to where I want to be, right? And there's lots of really fast algorithms for doing this. If you've ever played like a video game, these are the algorithms they use to make the bad guys move around. So we're trying to figure out what the lowest acoustic cost path is from where you are to where you want to be. And this is just sort of a demo of that in action. So here we planned a flight path that goes from Center City of Philadelphia to the American Helicopter Museum in Westchester. And the helicopter right now is on that red star along that path, traveling from the right to the left. That blue marked out area, that's some airspace that's closed for whatever reason, traffic, weather. And in just a few seconds, it's going to hop to another location. And we will, on the fly, try to generate an acoustically optimal path. At first, you can see it starts out a little squirrely because we cut some corners to get a path really quickly. But after a few seconds, right, you can refine this to get to what is really a low noise optimal path from A to B. A lot of other stuff that goes into this, right? We have to worry about how efficient is it going to be, what the impact is on passenger comfort, performance, et cetera. And that's why we're going to be working on this for the next 5 years. So I just to kind of wrap this up here, right, we have a few new acoustic tasks that are funded under the new VLRCO. Very excited about that. They kind of cover a full span here from predictions, noise measurements, and operations of vehicles. How can we use this data once we get it? And I think they're complementary in lots of ways, right? We're doing some measurements, which we could use to help validate and inform the predictions. We can use the modeling that we develop in order to help reinforce with this operation and path planning work. So in any case, that's what I have here, and thank you very much for the opportunity to share a bit what we're up to.
All right, thanks, Eric. And Ed, we've got time for a question or two. Oh, hold on, wait, Jose, wait, we need the microphone. It's coming up, other side.
Thank you. Eric, on your flight path simulation, what was the second box that showed up on the bottom? Was that an additional constraint?
Yeah, so basically here we've got a closed chunk of airspace, and it's just a square for convenience. And then, I guess I can't make it replay. But yeah, and then it'll move basically, so we're just moving the area of airspace that's closed, right? And then I have to reroute, I have to react.
Oh, I see.
To that.
So that could be a new block for whatever.
Yeah, it could be
want to avoid
airliners
this.
coming in, and you've got to close off some airspace. You know, it
Okay.
probably wouldn't look like that square, but that's just a kind of a toy example.
Will it be possible to keep multiple boxes, I'm assuming, too?
Oh, it could be in any arbitrary shape, yeah. Yeah, and you can have as many as you want. They can be volumetric, right? So they actually have altitude and everything like that.
Cool. All right, thank you.
Yep, sure.
Thank you very much. This is an interesting presentation. You got me thinking about a problem we have. And when you talked about these wind tunnels and having to geometrically scale a fixture to evaluate it, I was thinking about scaling like two bundles to evaluate flow-induced vibration.
Mm-hmm.
Is scaling a fixture such as the helicopter rotor blades even a tractable problem to geometrically scale it? Do you understand the dimensionless parameters and everything so that you can get a fixture that you can actually use at a smaller scale and get meaningful results for full scale?
Yeah, so there's and certainly for aerodynamics, right? And Mark Miller has a background in doing this. This is something that they have done for a little while for wind turbines, right? And you can think wind turbines are enormous, right? Nobody can afford to put a full-scale or even fifth-scale wind turbine into a wind tunnel, so they shrink them way down and then run them under compressed air. There are some tricks there, of course, because at some point, right, my geometry is getting so small compared to the real thing, I have to be very careful about how I manufacture things, right? And they'll do some other, surface roughness treatments and things like that to try to get the flow physics to behave in the right way. So there are some limitations because I can only build things so small. But yeah, they've shown very good results aerodynamically, and this kind of compressed air tunnels for like airfoil sections and things like that have a pretty long history. And then we've kind of moved on to other things, and we're trying to bring that back and then certainly look at it from an acoustics point of view as well.
Thank you.
Yeah.
Okay, we do have one question online from Mike Yang. Welcome, Mike. And he says, you'd stated the difficulty of using small-scale tests due to Reynolds number effects. How does this impact the large numbers of very small-scale tests in the lab that we see? Is the only value of those to validate predictive tools?
Yeah, it's a great question, and it really is going to depend on the flow physics that are dominant in that problem. So certainly if I wanted to just scale like the noise levels down or something like that, I'm probably not in good shape if I try to do that, right? Like the vortex core of an interaction between a vortex and a blade, it will be completely different at a different Reynolds number. And we have some experience. Another thing that, I think in the 70s and 80s people were playing with, and they found out some of the limitations of scaling for helicopter rotors. There's a lot of new energy in this area now, and people are kind of back to trying with small models, and I think there'll be some issues there. On the other hand, if maybe there are things like if I just want to know where the wake is going to go, I might have a little more flexibility. That might look in some ways a little more like an inviscid problem. I might be able to get away with things, right? And our hope is that you might even be able to do some correction where I can take a small scale experiment, but I know what the changes are going to be, what changes are going to be caused because I'm changing Reynolds number, and then I can correct that data in some way to get something that tells me a little more about what would have happened at full scale.
All right, great. Well, thanks again, Eric and Ed.
Great, thank you.